Okay.
So recording. So how it's going to go. Whenever you're ready.
Okay. 5-minute presentation starting in 3, 2, 1. Welcome to LB 273, Section 5, Group 7A's Formal Lab 1 presentation. Please note that Jagan Nalani was supposed to be part of this group, but did not show up or participate in the lab. So this is our experimental design. Our research question is how variation of height impacts the total energy of the ball as it bounces. And our procedure is fairly straightforward in Tracker, but it's also written on the slide.
Here we have the quantitative measurements of our experiment. The mass of the tennis ball we kept constant, and the variable that we decided to change was the height, and the different heights are marked by the different colors of the trials. Here we just have a few screenshots from the trials that we took in Tracker. And here are our motion maps for all 4 trials. As you can see, the arrows are getting longer to represent the increasing speed of the ball. And after the bounce, the ball changes directions and the arrows are getting shorter because the ball is slowing down.
All right, so now we're going to take a look at the schema. As you can see the schema, there's 3 components. First, we have the hand that drops the ball which comes in contact with the hand, and then the ground/earth, which is coming in contact as well as has a gravitational effect on the ball. Now, across all 4 trials, we see a similar trend in terms of how the pie charts shape out. However, we took 5 different instances before the drop. There's nothing but purely potential gravitational energy within the ball as it had not dropped and it's at the highest point. During the drop, this potential energy lessens and turns into kinetic energy. And for a brief instant at the ground, as it hits, there's nothing but purely kinetic energy within the ground. Now, the ball did not bounce to the initial height it was dropped at, and this is due to the fact that there's a transfer of energy from the ball to the ground, which comes in the form of internal energy, as you see during the bounce. So the ground takes some of this energy, the ball bounces back up, and increases its potential energy and lessens its kinetic energy. And at the peak of the bounce, there's nothing but gravitational potential energy found within the ball. However, there will always be that sliver of internal energy that was transformed into the earth as it contacted the ball. These are just the key points from what I just mentioned.
Here we have the position versus time graphs for all 4 trials. The graphs show the position of the ball at a specific point in time. As the ball is reaching the origin, you can see that it is increasing speed, and after the bounce, you can see the ball decreasing speed as it heads towards its max height. Here are velocity versus time graphs for all 4 trials. The velocity is negative at first as the ball is heading towards the origin, which we marked as the ground. And as you can see, the velocity changed to positive as the ball heads away from the origin after the bounce.
All right, now for acceleration, we only showed 1 graph because in free fall, it is constant at 9.8 meters per second squared. However, since this was dropped, it would be negative in this case. You see the peak of positive is when the ball bounces as it briefly shoots up and then goes back down to its negative 9.8 meters per second squared as it slows down.
These next 2 graphs are height versus velocity squared graphs for the drop and the bounce portions of the experiment, respectively. Velocity squared is used in calculating kinetic energy, which is why we chose to show it here.
All right, now we're going to take a look at the calculations. In order to do calculations, we used 3 pie charts that were key, as well as some equations shown on the top of the slide. We see that we use potential energy from before the drop, kinetic energy at the ground, as well as the peak bounce. In order to use these, we determine the total energy of the system. We determine the velocity and impact as the ball hit the ground, as well as the internal energy loss by using both the potential energy at the initial drop, as well as the potential energy at the peak of the bounce. We took the difference between those in order to find the internal energy for the system. A few calculation conclusions were total energy and velocity. As height of drop increased, the total energy of the closed system increased as well. The tennis ball dropping from a higher elevation resulted in a greater speed at impact with the ground. Now, with energy and with respect to bounce, contact with the ground upon each bounce resulted in a transfer of energy. A fraction of the tennis ball's kinetic energy is relocated into the ground/earth with every bounce, which takes form as internal energy in the system. Thus, the tennis ball will continue to bounce until all of its kinetic energy has been transformed into internal energy within the ground.
This next slide is a discussion of our experimental flaws. Most of them are due to Tracker, but there's also one that has to do with human hands dropping the ball from the correct height. This slide also includes a discussion of how we tried to minimize these errors. Next slide, please. This is our quantitative estimate of percent error using experimental and theoretical drop times calculated with the free-for-all equation and the data from our experiment. This is fairly normal except for the 0.25 trial with 34.1% error for unknown reasons. Thank you for listening. Was anybody timing?